This afternoon, we're going to cover some of the work of 3 of the AEF project teams. We'll start off firstly with Alexander covering the work of the medium voltage team. Then we'll be followed with Dave Smart talking about the work of the high-speed Isobus team, and then finally we'll be joined by Johan Witt, who'll be speaking about the wireless in-field communication team. These teams have they've been very busy. They've been doing a lot of work, and in 20 minutes or so, it's only enough time really to give you a high-level overview. But hopefully it will be interesting, and obviously if you want to know more, you can always reach out to us via the AEF website. So that's the introduction. Sorry, it's Andrew Oliver here again. I'm the leader of Project Team 6 in the AEF Communications and Marketing. I'd like to hand over to Alexander Schultz-Storz, who is leading Project Team 12, the medium voltage team, to give us an overview of their activities. Alexander, can you hear me?
Yeah. Yes, I can hear you. Andrew, thanks a lot for the brief introduction. I tried to share my screen in a second.
I'll tell you when you're in presentation mode. I can see the screen, but it's not my presentation. Yeah, that's it.
All right. Now I think you can see, and I go through the presentation. So welcome again. My name is Alexander Schultz-Storz. I'm leading the PT12 medium voltage team of the AEF. I'd like to provide some insights about the 48 volt. So that's why we call it 48 volt insights. So let me start. So the agenda is a very brief introduction of myself, then the medium voltage market insights, agriculture equipment to give you some impressions, the past, today, and in the future. Energy need examples. You wonder how much energy is required from the agriculture equipment, implements, and the trailers. Some use cases, power classes, architecture images, then an application matrix, which goes a little bit more in the deeper sense of the electronic design, and a summary at the end of my presentation. So first, a brief introduction. My name is Alexander Schultz-Storz, working for Panasonic Industry in Munich. I'm a mechanical engineer and an MBA, worked throughout various roles in the automotive supply industry, and since 2017 as a director for the division called Cross Value and Open Innovation. So we look at many changes in industries, mega trends, mainly in the area of IoT and electrification. That's in brief about myself, and you can see that as well in the slide deck. Then medium voltage market insight. So the AEF said the power requirements for implements are increasing continuously, and that's pretty sure. It's here mentioned sensors, actuators, but of course a lot implements need that huge amount of power. That means here a new power interface, which is a rated voltage of 48 volt, could be a cost-efficient solution for the majority of use cases. So this power interface will connect the tractor with the implements and the trailers to have the safe and always available connectivity. You will see later on it's going up to 10 kilowatt power. Where is 48 volt commonly used? It's coming from the car industry, in the motor vehicles. It's an onboard power supply. It's derived from the VDA to an ISO 21780. It's a baseline for many 48 volt power units in cars. In cars, it's used as in the car. So it's not a connectivity for 48 volt to the trailer, or even when you go to trucks, it's in a truck, in the towing machine, but not in the big trailer. So here it's a baseline. Here we are very thankful to the car industry to have this baseline introduced. Many components are available from that. So you see, baseline is there, and the need in the agriculture field is as well there. So this is a glimpse or snapshot of tractors. In the left-hand side, these are tractors from the 50s, 60s, 70s up to the 80s. A lot power was generated with the combustion engine, then transferred to hydraulics or pneumatics or having a 12-volt socket. In the middle, you see tractor examples from the last Agritechnica show. Looks more like very powerful machines having what you we will hear later on from David. It's about Isobus and Tim. So they are very high level of connected. They're running partially autonomous. They have GPS and so on. So it's really the tractor today is pretty different than the tractor in the past. On the right-hand side, you see again snapshots from the last Agritechnica show, where you see future tractors. On the top right, it's a tractor without a cabin. You see tractors with hybrid powertrains. You see tractors running autonomously, and on the bottom, you see even agricultural robots. So there's a big move again, past tractors, today tractors, and then a look into the future. Then on the next slide, you will see some implements. Let's say I called it here mechanic, today in the future. So on the left-hand side, it's an analog control. Let's say there is the prop shaft, you have hydraulics and maybe 12 volt, and that's, call it analog. Then nowadays you have mechanic and electric. Electric is the 12 volt system. You have section controls. The picture at the bottom shows a sprayer, and the white triangle there was already spray, so they can shift according to the section requirement. On the right hand side we see something named 48 volt systems coming from the cars. You see highly advanced technology. In that example, you see at the bottom a picture again from the Agritechnica show. It's a tractor with electric power control. So it's on the tractor itself, like in a car. It's a power source, a new voltage level in the board net, plus energy source for trailers and implements. On the next page is a snapshot I like to guide you through towards autonomous tractors. So I said before, the tractor today is already running with GPS, with stereo cameras. So on the top left, you see a stereo camera to identify the plant rows. You have individual controlled, section controlled devices. And in the tractor, the cockpit looks like quite advanced with a lot of displays. And yeah, the buzzword here or the technology applied is Internet of Things. So in all that technology, cameras, displays, section control needs energy. And according to the data we received, it's up to 5 kilowatt you already need for the autonomous guided tractor. So it's really amazing what energy is necessary. You need some redundancy, and you have to apply functional safety measures to safeguard that energy supply and the running system throughout the operation of the system. Then I was briefly announcing, we showing some use cases. So on the left, you see the tractors. They probably are the power supply. The power supply is available in the future in the front or at the rear. We wish to have for the implements 10 kilowatt constant power output. At the bottom, you see a picture how it can look like. Then on the implement side, we mentioned here seeding, harvesting, fertilizing, spraying, and plowing. These are some typical activities the farmer has to take over. And you see in the seeding area, when you have a 24 raw seeding unit, constant 10 kilowatt is all right, but peaks are already going to 15 kilowatt. So when you have on top the autonomous driving, there's a massive amount of energy. In harvesting, you see a similar picture, 10 kilowatt. Fertilizing, we had examples from implement makers. They say 10 to 100 raws 50 to 100 watt power is needed, multiplied by up to 48 rows. They would love to have 5 kilowatt. In the sprayer, similar, 48 rows, 10 watt each sprayer and constant 10 kilowatt. Plowing is not yet in the scope, but we learned there are some exercises and some studies at universities even to support plowing with 48 kilowatt networks. Then this is more dive into the technology side. So we say the medium voltage power classes and the connector is designed for 5 kilowatt maximum power. We go for a low power class, let's say, to have a easy entrance into the system. This is the minimum power 5 kilowatt available at the tracked output. High power class means 10 kilowatt available. Then we discussed a lot about power distribution. So we can say we have an outlet in the front with 5 kilowatt, an outlet at the rear side of the tractor with 5 kilowatt, or we go for just one with 10 kilowatt, and the locations we predetermined are front and rear. But the ultimate goal is to have one connector design for low and high power classes, and independent whether the connector will be at the front or the rear side of the tractor itself. Then how the image looks like. So the basic system, that's a snapshot from the draft specification we are writing inside the AEF organization. This shall be later on the blueprint towards an ISO standard. At the bottom, you see a picture of an connector example. You see the tractor part, very robust, very strong. On the implement part as well. On the top right, again, you see the connector appearance in the picture. So it must be really very robust, safe, and please imagine you have 10 kilowatt, 48 volt. So it's up to 200 amps, and we need to safeguard towards arcs and failure. So it will be a quite robust design, much stronger than the simple left-hand side picture or the 12-volt connectors you probably know from the different machines. The application matrix I want to touch upon. So we have a basic communication. This is given and safeguarded by the interlock function and the interlock pins. So when the interlock says yes, it's coupled, we can let's contribute the low power or then the high power to the implement. When there is more complexity, we call it smart communication. So we have the basic communication with the interlock, and then on top of that, we offer the Isobus. So then you can see by this application matrix, we can have a low power entrance system with a basic interlock communication, or we can have a high power system with a smart connector, which is the Isobus plus the interlock. So we can have, let's say, affordable entry systems, and we can have high-end and complex systems for all circumstances on the required scenarios. Then this guides me to the summary. Let me go through the 4 bullet points. So medium voltage at passenger cars are successfully developed and introduced to the mass market. That's pretty true, and it's commonly named as mild hybrid. And that's, of course, including dual voltage systems, 12 volt, 48 volt, and dual energy storage systems. The mild hybrids are, they started with 12 volt start stop, but now in 48 volt area, they go up to 10, 20 kilowatt power to assist driving and to have electric driving. So this is commonly developed and in use across the car industry, let's say North America, in Europe, in China, Japan, Asia. Then multi-voltage at 48 volt will provide the energy required. Medium voltage at 48 volt will provide the energy required for digital farming. So these 12 volt systems cannot provide the 5 kilowatt for digital autonomous driving, nor 5 or 10 kilowatt on top for the implements. So 48 volt will be a safe area, more easy to handle compared to a high voltage system. So 48 volt, let's call it a sweet spot for those applications. So 2 power classes and 2-step diagnosis will enable an entry system as well as a complex setup. So this is what previously shown on the use case matrix. So it gives provides some building blocks, and according to various needs in the industry, this can be matched. Then from the medium voltage working group, I can say 48-volt tractors and implements are planned to be ready for the year 2023 to 2025. There are plenty of requirements from the implement side. The tractor makers working hard on that. So that's an area where we see the market introduction of the 48-volt medium voltage systematics. So with this summary, I like to conclude the presentation where you could see tractors in the past, today, and tomorrow, some advanced implements, and you see with the paving the passes, let's say, by the car industry, this voltage level and ISO standard is available, and we build on top of that. Thank you very much for listening to the presentation, and I hand over again to Andrew, I guess. Thank you very much.
Thank you, Alexander. That was very informative, very interesting. Just a question, very briefly, how much can you borrow from the automotive sector on their work with 48 volts? Are there many things that could be brought over to ag, or not too many?
Yeah, let's say thank you, Andrew, for the question. This is a big part. So we cross-reference to the one ISO standard. That's true. The story goes from the car basically to trucks and to heavy trucks. They are having 48-volt systems as well. So from the car, they are more ruggedized and more robust, more powerful for the truck industry. And we are now relying on some components from the truck industry, which is going to 48-volt as well. So this is the evolution from car to truck to agriculture. But what is really more complex and more demanding in agriculture, you have the tractor, and then you have hundreds of different implements. The truck is a single close coupled truck, or the car as well. And here we really need to connect high power and the voltage and all the stuff. So it's good to have the base, but it's turning out to be more complex.
Okay, so it's all about the connector then. Okay.
Yes.
Thank you, Alexander.
Thank you.
So now I'd like to hand over to Dave Smart. Dave Smart is the leader of Project Team 10, the high-speed Isobus group within the AEF. And Dave, it's your turn to give us an overview of what's going on in the high-speed Isobus area.
Okay, thank you, Andrew. High-speed Isobus is Project Team 10 in AEF, and I don't have a slide to introduce myself, so I guess I'll just mention briefly that I just recently retired from John Deere after 41 years, so it's been a good long stretch there. But I continue to have so much fun with the industry work that I did for the last nearly 2 decades in Deere, that I've continued that work and continue to lead the work of Project Team 10. So I have some experience with Isobus and in this development of the next generation. So quick look at the agenda, and we'll go ahead and dive right in to give you an idea of where I'm at on that. You can keep an eye on it in the top right-hand corner. So brief history, and Isobus is kind of the nickname for the ISO standard, which is ISO 11783. That is developed for agricultural products. It's based on controller area network. And one of the things that really dovetails into this new work is the speed of Isobus. In the 90s, 250,000 bits per second of information seemed pretty fast compared to computer modems of the day. But now that we're in 2020, there's areas where that becomes quite a bottleneck for performance. But along the lines of this Isobus, the CAN-based Isobus, there is a lot of functionalities that it developed and made available for customers. The universal terminal in the ISO standard is referred to as virtual terminal through AEF UT, or universal terminal. That became readily available starting in about 2005. And then task controller, that really, precision farming control and data logging, launched in about 2010. There was certainly work on each of those for a number of years before it was market ready. There's been other regular enhancements, updates, and new functionalities. We've already heard a mention of some of the automation that's available, and so that's in many systems today as well. Around 2012, some of the companies recognized that the speed limit of the controller area network was going to get in the way for advanced systems. While it works fine for many, many systems today, and in fact, many systems have enough, they will fit within the capability of CAN for many years to come. So there's no real easy forecast to obsolete the existing network. But for much more advanced systems, that's where we really see the bottleneck of CAN, and we need to overcome that. So with that kind of brings us to, where AEF and Project Team 10 high-speed Isobus comes into play. So if we do take a quick look at, legacy, and legacy in this context doesn't go quite as far back as we've heard previously, but we're just looking at the Isobus, CAN-based Isobus systems. So we have a network that can traverse from the front through to the back and onto implements. It has connected electronic control units. There's a tractor ECU, which helps the tractor and implement coordinate based on ground speed, PTO, and other parameters. In the operator station is the virtual terminal or universal terminal that is in virtually every tractor today. And so that was, kind of the today's scenario. So with the realization that we need a way to break through some new bandwidth models to get much higher performance, this faster Isobus, and that's the HSI, is high-speed Isobus, is the name for Project Team 10. So what are we trying to do with that? We want much higher resolution of control. With CAN-based Isobus, it's pretty common that you can control sections or the whole planter, the whole sprayer, and maybe 2 to 5 sections within that piece of equipment. But we really want to get down to both row or nozzle level control and at a much higher level of control, much faster ability to control that for more accurate placement of the material. From a user experience, a faster network would also give us the option for a much improved user experience on the universal terminals. So some of the base requirements to get to that we have taken in Project Team 10 is we want to take advantage of industry standards. Just as the CAN bus originated in the automotive sector, we like that type of technology. It's robust, reliable, well developed by automotive, scales well into the ag area. And we need, of course, this higher performance. We need to, develop something that's future-proof. The CAN bus has been around now for well beyond 20 years, even in the ag sector, and since the 80s in automotive. So can we create a technology that has as much life looking forward in time as CAN has served us so far? And we're going to do our best to assure that. And we need this Isobus aligned architecture. So devices are going to plug in. There's going to be combinations of tractors and implements and in-cab appliances, both legacy equipment and new equipment. And we need the best way to take advantage of all of those. Through the high-speed Isobus team, we looked into what are our basic use cases, and certainly that command and control was right at the top of the list. That is, Isobus today, and that's what we need to certainly improve and continue on. We also looked at the technologies that are of high interest to customers, and real-time video monitoring is taking hold quite strongly. So we see a lot of want and desire to put cameras at the front of the machine, the back of the machine, even several cameras across the implement, and give the operator a chance to just watch the process as it's operating. And then there's a scenario with bulk data transfer, and I should mention the PT10 that you see after command and control, that's Project Team 10. Project Team 8 was a camera systems team. That team has folded into Project Team 10 for the high-speed Isobus, and we'll share the technology of the high-speed network with them so we can pass the video. And then the Project Team 11 is the wireless infield communications, and that's a scenario where this bulk data transfer, we want to deliver guidance tracks, coverage maps, and even prescriptions from one machine to another in a convenient manner, and that would be wirelessly. Project Team 4, service and diagnostics, and we have faced for decades the fact that not every OEM can convince their customers to buy only their equipment. So you see a lot of mixed tractor and different manufacturer of implements put together, and that creates the challenge of when things are not working right, what's the best way to get that solved? So there's a lot of attention in the research of high-speed Isobus to improve upon that and reduce the downtime certainly, and speed the time to repair. And then as we derive from that, some of the base requirements, we need this much higher performance, which translates into a higher bandwidth of communication. And we need a different level of real time than what we have with CAN, something that's much more reliable, predictable, and faster. And yet we want to continue with that existing architecture. So we've looked at a lot of different scenarios of technologies that might be suitable for this, and certainly the CAN-based technology that we're familiar with today, newer entrants to the CAN market, CAN FD is in automotive space, FlexRays in automotive space. We've also looked at various wireless technologies. Everybody is quite familiar with Wi-Fi technology for laptops and tablets. And along with that, we have also looked into Ethernet. And so with Ethernet, it's available in many speeds. You may have it connected to laptops in your home. More likely, you're on a Wi-Fi network, but Ethernet is very pervasive in industry. It's also readily available in automotive. One of the things that we have observed as we looked into this research is you can keep going faster and faster to a degree, but then as you push faster yet, you end up compromising the range or the distance that you can communicate rapidly. And our equipment is large. So when we see this greater than 1 gigabit per second Ethernet, it's available today, but the cables have to be short. And so we're trying to find the best compromise, gets us the most suitable scenario for taking advantage of this. So we have set our direction on wired Ethernet using an automotive Ethernet. So again, we get all the benefits of the automotive research and development and availability of components and suitability for our industry. So if we take another look at implement combination here with a system based on the high-speed Isobus, we would have potentially various devices scattered across the system. And within our team, we had research to simulate what would this look like, what would the capability of the system be, and how scalable is it? So knowing what we know today, how much headroom do we have for next year or the next 5 years, the next 10 or more years of ongoing enhancements and developments to that. So we went through quite a bit of work to do some analysis on that and find out, is there the right solution readily available for us? And what would that solution be? We looked at many different scenarios. So with that, we came to the scenario where we're focused on the automotive Ethernet, which is one single twisted pair of wires somewhat similar to what you see with a CAN bus today with a twisted pair. It's a little bit higher quality cable and connection requirements for the Ethernet because of the extra speeds for that. But we're working to finalize our architectures for kind of a minimum, typical, and maximum system of devices, components, capabilities, connections. From a physical layer perspective, we have selected a connector that is suitable, and we're working with the supplier on that to have a very reliable interface. We're working with harness cable providers for the data and power that will traverse the network. And because it's Ethernet, if you're not familiar, that is commonly connected to network switches, which provide the traffic management across the system. So that becomes part of this base architecture. From a protocol perspective, we want to meet many of the same objectives that we have today. You want to be able to just plug the equipment in and the electronics discover each other between the tractor, the in-cab, aftermarket appliances, and the connected implements, and find a way, through this ISO standards that we're developing to become a system that's certainly more than the sum of its parts. Isobus tunneling is mentioned there. That really means don't forget about today's Isobus. That will continue forward and will provide support for that mechanism, whether wired independently with CAN, as we do today, or integrated into this Ethernet as kind of a tunneling mechanism through the Ethernet protocols. And we've looked at many different industry standard protocols, and again, looking to find the most suitable for our industry and most scalable and able to carry us for the next decades. So we also collaborate with similar industries. We have connections to earth-moving machinery. We have connections to over-the-road tractor-trailer systems that are in development. And we're all in kind of the same situation of looking for the best solution, working together to ensure we have the best one for our industry, and what's compatible with those other industries can benefit all of us as well. Ultimately, what do we do within AEF? We publish some guidelines. We'll have guidelines on the basic architecture, similar to what you saw in the diagrams, much more detailed guidelines to the components that can be permitted and the connector characteristics and cable and so forth to ensure the most reliable and deployable solutions. And then standardized protocols so these devices can be plugged in and work well together. From that point, we hand it off to an ISO standards group and work with them to turn it into deployable standards that the rest of the industry will pick up. And many of the people working within AEF will also be participating on that ISO standards group, so we'll have a nice smooth transition of the knowledge, research, and guideline information into the standards. So if we take an outlook into what a future system might look like, we start with today's CAN-based system, and we add into it the Ethernet technology that we were talking about. And it looks, very much like here's another complete system layered on top. And at least initially, that is probably true. As we continue to develop this, we are developing it so we can continue to add new capabilities and protocols and introduce cameras and the wireless in-field communication. And with a noble goal that CAN becomes less necessary, that does not mean that CAN goes away, because many systems can take advantage of CAN and meet all the requirements. And it's quite frankly, it's a more cost-effective solution. But where you need this higher performance capability, where you want or need the remote viewing camera systems, then you have to have a new technology. That's the first place where this will come into play and show up. And with that, I have wrapped up. I think I met my time quota, Andrew.
Yeah, well done, Dave. I didn't think you'd do it, but you've managed to stick to the time very well. Funnily enough, I just have a quick question for you. You showed the slides on the simulation, and to do that simulation, did you analyze all sorts of different use cases and work out what sort of loads would be on the Ethernet? Is that how that worked?
Yeah, we applied the simulation to several different technologies, both wireless and Ethernet, because we hadn't fixed our direction at the time, so we were still in the exploratory phases. As we focused on Ethernet, then we went into much more detail. But in both of those scenarios, we started with an imaginary future implement. Take what we know today about, among the most complex implement and needs. And then as a group within PT10, we tried to imagine, 5 years, 8 years from now, what are the requirements for a new advanced implement? We want, seed placement and per row and the ability to control that per row. Or from a sprayer, we want, the ability to only apply the chemical where you want it and avoid everything else. It takes much higher performance of control, much faster, much lower latency of control. And then mixed in with that is, let's put some cameras around the system and see that there's a lot of video traffic sharing the same network with the command and control. And the wireless in-field communication, I think, is not represented by a little block in this diagram, but that type of data transfer from machine to machine was also included in the analysis. So we had a university team that did a lot of this work for us and had the tool set and the skill set to create those simulations and evaluate, can they fit? Do the real-time needs, are they met? And and if we continue to add more and more and more cameras and electronics to the system, at what stage does it begin to degrade? And we understand that as well. So that's a lot of the work that came out of that simulation.
And that's what ultimately led to the decision that Ethernet is the right approach.
Yes, yeah. The real time, the goal for our real time demands really led to a wired network rather than wireless. And then with Ethernet, there's many different speeds of Ethernet that are available from an automotive architecture and market perspective that are most suitable for our industry. And with the cameras and the wireless in-field communications, that really drove us to this 1,000 megabit per second or gigabit Ethernet, which is about 4,000 times faster than today's CAN bus. And even as we imagine these future implements, they don't consume all of that bandwidth. They consume actually a fairly small percentage of that. So that gives us a lot of headroom for the things we did not yet imagine, or the things that might be imagined, 6, 8, or 10 years from now, and they need bandwidth, and we have it available.
Great. Okay. Thank you for that. It was a great presentation, and it's nice to understand the decisions, the reason behind the choice for Ethernet, and it sounds like it's really got a lot of, it's future-proof, shall we say.
As much as we can predict the future, and then hopefully a little bit beyond that.
Great. Okay, thank you, Dave. I'd now like to hand over to Johan Witt, and Johan is the leader of Project Team 11, which is the wireless in-field communications group. Johan, can you just give us an overview of what's going on in your project team at the moment? We can see you well. We can hear you.
Sure.
That's good.
I have to share my screen a second.
It's always a challenge with the new systems. Something.
Okay.
Yes, you're in presentation mode. Take it away.
Okay, perfect. I would like to show up a bit about wireless in-field communication for direct machine-to-machine communication, and I would like to start with a small introduction of my person. So I'm head of advanced development electronics in the business unit Grain of class. I'm based in Hasewinkel in Germany, and I'm member of PT11 since the beginning in 2015. and I'm the team lead since 2017. And looking a bit deeper in the project, I would like to start there with motivation and use cases, then go on with a deep dive in our technology, and ending with a short summary. So when we are looking at our big picture and the boundary conditions resulting out of this, you can see here in this picture a farm which could be located everywhere on the world. So we are seeking for a solution which is worldwide available and applicable due to the fact that our market is all around the globe. And we have to deal here with a situation that we are mainly doing our operation in rural areas, and that we have also a lot of applications where we need real-time communication, and that means for us that we need some infrastructure-less communication, so we cannot rely on any kind of cellular-based communication, cloud-based communication. It's not all every time, everywhere available. And it's also difficult to meet our real-time requirements with having there someone third in the middle of our communication path. Usually we have to deal there with mixed fleets. I think Dave pointed this out as well. So we see there a lot of different brands working on our fields in cooperation with each other. And so interoperability is an absolutely need for our inter-brand communication. When we looking there on the farm and seeing all the machines doing their work, we started in the beginning of the project team to collect their different use cases. So most of these different types of works are connected with a different demand on communication. But we are quite sure that standardized machine-to-machine communication is really a key enabler to add their efficiency to our work on the farms. From a point of quality, from work quality, but also when we are looking for some safety issues there. And in the beginning, we collected all these use cases. I think it was something about 30 different use cases. And then we start their analysis to see what is common with these use cases and what is different. And in the end, we came up there today with 4 different use cases. So first one is what we are calling process data exchange, which is typically something like you want to exchange your AB line between 2 machines, or as shown here in the small picture, when you're doing there with 2 machines work on the same field and you want to share your coverage map. So being able to see where the other machine already did their work and to avoid that the same piece of soil is worked twice. And so when we're looking there at the requirements, we see there quite a high range requirement. So in Europe, typically up to 2 kilometers. The guys from the US saying, okay, we would like to have there maybe a bit more, depends a bit. We're seeing there a bandwidth requirement, which is not totally high. It's what we are calling medium. So maybe 1 Mbit or something in that range is required there. Average is with this use case not that big issue due to the fact that it doesn't make a big difference if the coverage data is transmitted within milliseconds or seconds. That doesn't make that big difference. And we have here always a relationship from end to end. So we can have one sender sharing data with many receivers and vice versa. The next big use case is what we are calling cooperative machines. The automotive guys are using the wording platooning for that. So typically when we are looking at agriculture, that are this unloading use cases where a combine is unloading grain to a tractor with a grain cart or something similar. But it could be also when you're looking a bit into the future that we have one tractor with an operator and the second tractor following the first one. And the difference to the first use case is here that we have here a strict control-orientated use case. The first one is more data-oriented. We want to exchange data. Here we want to exchange more or less control commands. From a point of requirements, we see here a much lower range requirement, so maybe up to 50 meters or so. So we expect that the machines will operate close to each other if there's a control required. The bandwidth is quite low, so it's below the speed of our today CAN bus systems. You only need there some control data transmitted. It's not that much, but the latency requirement is quite high. So we really need a low latency of maybe 10 to 50 milliseconds somewhere in this area to make this use case working. And we see there always a one-to-one relationship. So maybe there's one master controlling more than one follower, but this will be always then many one-to-one connection. The third use case is what we are calling high volume data streaming. So typical application where we want to do a video stream of a camera from a first vehicle to a second one. There we see a range requirement somewhere between the first and the second use cases. The bandwidth is quite high, and then maybe some of you will say, okay, but there is a possibility to compress the data. But when we are looking at the latencies, we see there a requirement that we have to transmit the data within 200 milliseconds from glass to glass. So that means from the camera to the screen. And so for the communication part in between, there's even less time available. And so compression will be difficult to do it within this time. And so we need there some bandwidth. The last use cases is related to the technology we want to use. I will come to it later, and that is about road safety. So we can use this communication technology to make other passenger cars, trucks, whatever else on the road aware of what we are doing with our machinery. So if we want to enter the road or we want to leave the road to a field, we can send out a message saying, hey, I'm wanting to do this or that, and all the cars around could receive this message and maybe show up a warning saying, okay, please slow down, there's a tractor entering the road in 100 meters, and doing there some road safety stuff. So having a bit more deep dive in our work, coming up to the radio technology, as we have seen before, we need a long-range, robust, infrastructureless radio technology, and the technology should be available. So it doesn't make sense for us to look in the future, and hopefully there will be something within the next 10 years which maybe could fulfill our requirements. We want to use something existing and, if possible, proven solution, and will reuse this and doing maybe some tailoring to our use cases. And so our choice today is that we want to use 802.11p as a radio standard. That is a radio standard based on Wi-Fi technology, but it's a bit tweaked to be more robust. And it was mainly developed for CITS, so Connected Intelligent Transportation Systems. Maybe you have heard about it. So it's mainly about this road safety topic today, as day one use cases on the road, but they are thinking also about efficiency topics there. We have there available, coming with this radio technology, some high layer protocols, DSRC in the US and ITS-G5 here in Europe, which will help us to having there some basic functionalities. We could use with this radio technology some spectrum which is dedicated for this use case, and which is quite nice because you have not to share it with two other members there or participants, but it's also applicable in the ESM band if required. So we are quite flexible there. To make sure that this radio standard is feasible for our use cases, we performed a test to see if our use cases will work with this radio standard. And in the upper right corner, you see there a picture from this unloading scenario where we did some tests together with the University of Paderborn. And if you like, I put here in the link and you can download there's a paper giving you a much more deep insight into the radio technology and the results we gathered there with the field tests. To show up that road safety is possible with our machines, that we can participate there on this existing CITS system, we set up a prototype, and this one was shown on at the IoT Week in autumn 2018. And the basic idea was that we gathered data from the Isobus and shared this with a passenger car using 802.11p as a radio technology. And so it was a direct communication between the tractor and the passenger car without any infrastructure required. And so we were able to show up a warning in the car when the tractor starts to moving on the road or want to leave the road. And that would be a possibility to avoid their accidents in this use case on the road. But we also are spending their work on our platooning use case. So maybe you know there are a lot of research activities within the last 10 years or even longer. So Fendt showed up with this use case where a manned machine was a leader and the unmanned machine was a follower some years ago. Klaas also showed up with a platooning solution for forage harvester and tractor trailer from a research project last year where we are using 802.11p based communication for that. And right now we are discussing there how to align with on-road platooning projects. So the truck industry is there quite busy and discussing how we want to solve this problem, if we want to use centralized or decentralized approaches, how a message set is looking, but we are also discussing safety aspects. The use case process data exchange, maybe as you know, today a lot of the exchange of data is done via cloud or even with USB storage devices. And there are some multi-vendor solutions available today, which are mainly proprietary. And so we plan to have this direct infrastructureless exchange of this data in near real time. And we have to deal there with some challenges like this limited range. We have to deal with that messages could get lost while transmitting them. So we have to take care for data inconsistency. And so we have right now a project running together with the University of Saarland and our project team to do some work on the workgroup management and also on data exchange and synchronization strategies. Coming to a summary. We want to use proven and already in use automotive technology, and we found this with 802.11p. And we see there's a need to enhance the standard a bit to fit to our agricultural use cases, to make it much more easier for anyone who wants to do some implementation of wireless in-field communication. Our goal is to build their COM middleware, so to provide software which could be used for machine-to-machine communication. And we are also looking out to have road safety in scope, being able to participate there in this ongoing development in CITS systems on the road. So being able to share data there with passenger cars, trucks, to avoid any incidents with our ag machineries. So how far have we come to this goal? So first one is we made this decision on the radio technology. We started their cooperation with the Car-to-Car Consortium and ETSI as two players which are really important for standardization in this area. We did this field test to show up that the technology we want to use is suitable for our use cases. We are working on prototype and guideline implementation for process data exchange and platooning. And so our scope in near future will be that we will start this implementation of the common software, including security and safety measurement. So we must ensure that we can use our communication also in safety, functional safety relevant use cases. And we have to ensure that the data will keep private when we are transmitting this kind of data over the air, and therefore we need security. And coming with the software, we will also start to work on application definition. So how will look a common coverage map sharing or platooning solution in the end for our customers. And when we are looking a bit more in future, we see there are new upcoming radio standards like 5G, 3GPP, and we will have this in scope as well to ensure that we will have their long time compatibility to this new upcoming standards and being able to switch to them when they are really ready and available for the market. So I would like to thanks to have here the possibility to show up users some information about our work in PT11. And so if you're interested, feel free to get in contact with us. And you're also welcome to join the working group and to join the project team and add there your ideas and experience. It would be great if I can see some of you in one of our meetings. So, Andrew, thanks a lot.
Johan, thank you for that very informative presentation. Just a quick question from my side. You mentioned that as far as the coverage map sharing, the range requirements between here and North America was slightly different.
Yeah.
So yeah, the range between 2 and 6 kilometers. Wow.
Yeah.
Okay. Can that be managed with the technology today? Or?
So I'm quite sure that when you have the really big flat field, you will definitely be able to transmit more than 2 kilometers. I would say 6 kilometers could be challenging, but you must also think, is it really necessary to have the communication all the time when you're working on the different ends of the field? So maybe it's also enough that you can share data when you're coming closer to each other again. And so I wouldn't see that as a really big point that we will not be able to come up to 6, but maybe to 4 kilometers or something like that.
Okay. No, that's great. Yeah, understand. Okay, thank you, Johan. So I'm just keeping an eye on the time, and I think we're going to get cut off pretty quickly. So I'd just like to thank the speakers today, Alexander, Dave, and Johan. Hopefully, all the participants have got a bit of an understanding of what's going on with these different project teams, and really, it's a good indication of how the AEF is working on electric and electronic issues or communication issues, between tractor and implement, and also up to the cloud. So we've really expanded our scope beyond just this Isobus communication. While it's very core to what we're doing, we've got this really good cooperation between all the different companies in the ag industry, and we're using that cooperation to further this work in other areas of electric and electronic compatibility. So I think it's really encouraging that this cooperation is going on, and I think it can only help the whole industry in the future. with that, I think we need to finish this this meeting. So I'd like to say thank you very much once again to the presenters. Do we have time for one more question? No, I think it would be dangerous. We're going to get cut off. Oh, Alessio?
Hello, I don't know if we have some couple of minutes more, but let's try. We have a question about which is the provision, the forecast for which will be the main actuator using electric power in the next future, or maybe yet today. This is for Alexander.
Can you please shortly repeat what is the?
Which are the main actuators that, in your vision, will be the first one to become electric, full electric in the next years? Or
okay, let's say. So I understand the question: how to move to full electric. So let's say the mid voltage project team is a medium voltage team which is going to the, let's say, mild hybrid, which you have in the car. So it's a kind of hybrid system in the tractor. And this is the good solution for all the implements. When you talk about full electric tractor, it's probably going for the high voltage tractor systems. This we probably see first in the municipal tractors or the smaller tractors for in-city use, and then probably coming more to the real field. But for the big tractors, you need a massive amount of energy, and that energy storage is quite a headache. So first we go hybrid, and then in-city use, and then probably going for the full electric.
Well, the question was mainly related to the implements, which will be the main actuators today using...
The implements first we see for the medium voltage are sprayers, where you have high-end nozzles and fertilizing. So these two areas are the first we see. Yeah.
Okay. So I've been told that we need to close right now because there's no time. There's the new webinar waiting for us. So thank you from my side as well, and well, thank you to all the attendees today. Need to close. Bye bye.
Thank you.
Bye bye.
All right.
Bye bye.